So we're here with Jim Trainham, the Executive Director of the Research Triangle Solar Fuels Institute. Jim, the Research Triangle Solar Fuel Institute has 4 parents, RTI, Duke, State, and UNC Chapel Hill. What does each parent contribute, and particularly financially? Do you have an annual budget?
Yes, I do have an annual budget. They all contribute money as well as people. So people are part of the formation of the Institute. So there are certain professors who spend some time working with the Institute. And the great thing is that it has enabled certain professors across the Triangle to work together that did not even know each other before we formed the Institute.
Give me an example.
Well, for example, Jeff Glass at Duke and Professor Gregory Parsons at NC State.
And how do they work together now?
Well, one develops nanostructures, and the other puts catalyst on the surface of those nanostructures.
Okay. And they did not know of each other before?
They didn't know each other before.
Okay. And what is your annual budget, ballpark?
Right now it's running about a little over $2 million.
Okay. Yeah. But you don't have the people here. They are remaining at their...
No, actually we have lab space here at RTI.
Okay.
And there are Institute RTI employees who do work full-time.
Okay.
Part of the budget that we set up are fellowships that will support students and postdoctoral fellows to do work here at the Institute, so that there will be joint students or postdocs work being done here at the Institute or in the outlying institutional laboratories.
Okay.
Okay.
And if I get this right, you're trying to make solar fuel by splitting water into hydrogen?
That's correct.
And I take that this process is done in what you call the sunlight capture panels. Are these solar panels, or are they just called something else? And explain the technology and its challenges.
Okay. Well, first, they're not exactly the same as standard solar panels, though the photoelectric effect is still used. In other words, one particular technology uses semiconductor-based electrodes, and the semiconductor in this case is essentially the same as in a photovoltaic cell.
Okay.
You absorb the light, it excites electrons or holes, you get an excited electron. In this case, though, we want the electron or the hole not to recombine very rapidly, just the same way as what happens in a solar device. But instead of making electricity, we actually, that electron or hole is transmitted to the surface, and where we have a water interface or electrolyte interface. And there may also be a catalyst at that surface. And that high energy electron or hole then enables either water to be split. And you can also continue to reduce CO2 as well directly. In another generation, that would be possible.
What are the challenges of this technology?
Well, the basic challenges in all the photoelectrochemical devices for carrying out water splitting is, number one, lifetime of the device, and number two, efficiency. So it is embryonic compared to solar cells. It's not that these devices have been around since the work of in Japan of Honda, etc., in 1969. And there have been cells that have been developed that have very high efficiency, as high as 18%. So they're in the same ballpark as normal photovoltaic devices for making solar energy. The problem is that they don't last very long, because a lot of these semiconductor devices, they corrode in the electrolyte.
What does not very long mean?
Most of them don't last more than a day.
Oh, okay. Okay.
So obviously, if you really need for the economics to work, to either have something that's going to last as long as typical photovoltaic devices do, or they have to be able to be made cheap enough that you and engineered in a way that you could replace them very rapidly. But something that only lasts a day is not going to cut it. So we have to develop them that at least last a few years or more. But in that case, they'd have to be easily replaced and very inexpensive.
So your main challenge is material?
And main challenges are materials, and also materials in a number of ways. Not only would they have to provide the right chemistry, they have to be inexpensive and very plentiful. So you need manufacturing processes that exist, preferably at least in the shorter term, that you can actually enable yourself to get large quantities of materials, because to do fuels and make any significant impact, it's going to take square miles. And for example, we've done the calculations, and just to ballpark it, we burn about 9 million barrels of gasoline a day in the United States. That's 380 million gallons of gasoline a day. Now, if you want to replace all of that with solar fuels, you need the hydrogen. Okay, so to get the amount of hydrogen, that requires you to have on the order of about just under 15,000 square miles of these devices. Okay, now that sounds like a big number, but it's only the size of the state of Maryland and Delaware put together, which is less than 0.5% of the land mass of the continental United States. It's only a small fraction of the state of Nevada.
Right.
So it sounds large, but at least it's feasible. Okay.
And this area was in the running for the $122 million innovation hub, which went to what's called the Joint Center for Artificial Photosynthesis, which is Caltech leads that. Are researchers on the West Coast and the East Coast competing on this now, or are they collaborating? Basically, are you trying your own approach here and seeing how this goes, or are the two hubs working together?
Well, Tom Meyer, who leads the EFRC on solar fuels here at the University of North Carolina, and is the chief scientist of the institute. He's made a call to Nate Lewis, who is the head of JCAP, and they know each other. And a couple of years ago, Tom had a meeting of all the participants in solar fuels type technology development in the country, and everybody said that whoever won the hub, we'd all work together anyway. So that's our intention. We have some different approaches, because one of the things that we emphasize here is the translational part. We're I think have tremendous experience at scale-up. Okay, and so we will take anybody's science. Economics and engineering to show what is the best system, and then identifying the best system, we'll work towards scaling that up to a commercial demonstration. So I think that's probably more our focus, though we still will do some basic science, without a doubt. Tom's doing them, and also the work done at both NC State and Duke. We have some different approaches, but in some cases similar. But we will end up, I think everybody in the community will work together on this. That's the intent. That it's too difficult of a problem not to.